Okay, so we're back, and now we're just going to briefly go over effusion, diffusion, and then just the math of it. So effusion and diffusion all deal with the fact that gases naturally mix and that you can't stop gases from mixing. Effusion is why balloons deflate over time and why your tires deflate over time. So effusion is that if there's any small holes, because gases move randomly, eventually one or two or three of the molecules eventually is going to find that tiny hole and eventually escape. So this picture over here is showing you effusion. So a couple of these gas molecules are all bouncing around, and again, they're not going in any particular direction. It is a random motion. And every so often, just like a broken clock is right at least twice a day, every so often a gas molecule will actually go through that little hole. So effusion is that movement of the random movement and the escape. Diffusion is why you wear perfume or cologne, why you know that a skunk is nearby. Diffusion is that spreading of gases, and that when you have two gases, you cannot keep them apart. If you have hydrochloric acid at one end of a tube and you have ammonia at the other end of the tube, they'll actually meet, and where the gases mix, you'll actually get a white ring of the chemical reaction forming. And that's just something that you can't control. And it's actually kind of cool because they actually move in the ratio of their speeds, which is what we talked about before. The guy that came up with this was Thomas Graham, and he came up with the law. It's a really kind of crazy that the rate of effusion is inversely proportional to the square root of its molar mass. So basically, it's just an equation that he found out that works for it. You don't have to know the derivation, but all I did here is I have the first kinetic energy, I have the second kinetic energy, and the little ones here are just saying this is my first gas, this is my second gas. I'm saying they're at the same temperature, so I can set them equal to each other because they have the same kinetic energy. First thing that goes is the 1/2 because mathematically they're redundant. Excuse me. The next thing I did was I brought my masses on the same side and my velocities on the same side. Remember, the masses are molar masses and the velocities are in meters per second. And then what I did is I just square rooted it because that's the way Graham did it. I don't know why he didn't leave it with squares, but he actually had the square root here. And what you want to take note of is that your molar masses and velocities are catty-corner from each other. They are not on the same level, so just be aware of that. This is just showing you the effusion and diffusion. This first picture here shows you nitrogen and helium. They're supposed to be the same size volume. It doesn't, like we all know, helium floats and nitrogen doesn't. That's not what they're looking at here. What they're looking at here is that the smaller the gas, the faster you're traveling, and the quicker you should diffuse. So if you think of nitrogen gas, it has a molar mass of 28 grams. It's a larger gas. And helium only weighs 4 grams, so it's a smaller gas. So at the same temperature, same volume, we have the same amount of moles of gas, but the helium is moving much faster, and you can see that it effuses faster. So what that means is more of the helium molecules escape, and you can see that the balloon actually deflates faster, which is why helium balloons are really fun, but they're not the most practical thing because they do deflate faster. And then the next two slides are just different ways that you can do the Graham's law. So this is showing you, okay, what's the comparison of effusion or, diffusion even. So what I did here is I just set it up. I have sulfur dioxide, which is the stuff that smells like rotten eggs, versus oxygen gas. And I wanted to see how they compared. So what I did is I don't know anything about their velocities, but I know their molar masses. And I just made sure that they're catty-cornered from each other. And I said, okay, I don't know the velocities over here, but I know that oxygen gas is 32 grams per mole. And I know that my molar mass of sulfur dioxide is 64.1 grams per mole. And what I do is just do the math over here. And what you find out is that SO2 is moving approximately 70% the speed of oxygen. So you can see it's not a direct correlation because it's actually twice as heavy. But it has to do with the square root here. So you can see in relation to each other how fast they're moving. And also, if you know how fast one gas is moving particularly, and you know the molar mass of that gas, you can actually figure out the molar mass of another thing. Or you could actually figure out the average speed using this equation. So you can find the velocity, You can find the relationship between the velocity, the relationship between the mass, or you can find actually out the mass.